Welcome to our quick dive into software maintenance and evolution. Today, we are exploring how software is kept up to date and adaptable after its initial launch. From fault repair to functionality additions, we will explore or uncover the essential strategies that keep software systems efficient and relevant in a rapidly evolving tech world. We will also touch on maintenance predictions and software re-engineering, key processes for future-proofing and revolutionizing legacy systems. Get ready for an insightful session and do not forget to like, subscribe for more tech insights. Let's jump right in. So, starting with the first slide of our part 3 of chapter 9, is software maintenance. But what does it mean? Software maintenance, which is actually a crucial aspect of software engineering, involves modifying a program after its initial deployment. This term is often associated with custom software modifications, rather than generic products, which usually evolve through new versions. Typically, maintenance does not involve significant changes to the system's architecture. It's more about tweaking existing components and adding new ones to enhance or fix the systems. So, moving to the next slide, we here identify different types of maintenance. So in software engineering or in software maintenance, we categorize activities into 3 types: either fault repairs or environmental adaptations or functionality adaptations and modifications. So let's take every single one of them apart. First one, it's about fault repairs. This involves modifying the systems to fix bugs or vulnerabilities, thereby correcting any deficiencies in how the system meets its requirements. So basically, we are talking about some bugs or mistakes in the code. Maybe there is an open vulnerabilities that have been publicized, so we need to take care of it by fixing our code. This is the first type of maintenance repair, which is a fault repairs. The second point is environmental adaptations. Here, maintenance here is focused on adapting the software to operate in a different environment than its initial setups, like a new operating system or computer. So maybe we have moved our software to a different computer, different data centers, where the technologies may be different. So we need to change our software to get adapted or to adapt it to the environment or the new setup that we have. The third point is functionality addition and modification. This type involves updating or changing the system to meet new requirements or functionalities. Moving to the next slide, which is, as you can see, maintenance effort distribution. In this pie chart, we break down the typical efforts devoted to software maintenance. The largest slice at 58% here is functionality addition or modification. This is where we actively enhance the software to meet the new demands. Fault repairs account for 24%, addressing bugs and vulnerability, as you can see. And the last point is the environmental adoption, taking up 19%, involves actually adopting software to work in new or updated environments, such as a different operating system, as we said. Moving on to the next slide, which is about maintenance cost. Maintenance cost for software typically exceeds the initial deployment cost, potentially ranging from double to 100 times more, depending on the application. These costs escalate due to a mix of technical factors, like software complexity, for example, and non-technical factors, such as user requirement. So, over time, maintenance activities tend to degrade the software structure, compounding the difficulty as well as the cost of subsequent maintenance. Additionally, all the software, especially those reliant on outdated languages and tools, often incur higher support costs, as we have seen in previous slides or chapters. So, moving on to the maintenance prediction, you might be asking, can we predict these maintenance costs in advance? Probably yes. Let's see. Maintenance prediction focuses on identifying system components that may pose future problems or incur high maintenance costs. It evaluates how changes affect the maintainability of codes or components, acknowledging the system alterations can degrade the structure, thus reducing maintainability over time. Essentially, the more changes made to the system, the higher the maintenance cost. So this is like there is a link between the number of changes that we do to the system and the maintenance cost here. Once you increase the changes to the system, the cost will increase too. Moving to this slide, which is about maintenance prediction. This diagram illustrates the concept of maintenance prediction in software engineering. It is the process that involves assessing which parts of a system are likely to be affected by change request determining the potential costs of these changes and predicting how they will impact the system's maintainability. By understanding these factors, organizations can make informed decisions about when and how to update their systems. So, in the context of software maintenance and looking to these illustrations, predicting maintenance involves evaluating various factors, which has to come from such questions, for example. Each of these questions will give us some idea into maintenance planning. So, for example, which system components are most likely to be impacted by the changes? This actually allows us for proactive planning that will be amazing into figuring out software maintenance cost. And the second one is identifying parts of the system that will be costly to maintain, helps in a way in allocating resources in an efficient way. And that will help us, of course, into the maintenance process overall. The third, let's say, thing is estimating the number of expected change requests. You ask, why should we care about the number of requests we are having? We should be focusing on the change, how many requests we're receiving, because it will help us in capacity planning for maintenance teams, for example. Assessing the lifetime maintenance cost of the system will also ensure long-term budgeting for the whole project. It's not just the software is not going to be running for 1 day or 2 days max. It's going to be running for a long term. So we need a long-term budgeting. So if we don't answer such a question, we will not be able to set up any long-term planning. The other point is about predicting short-term maintenance costs. This is beneficial because it helps us to plan immediately from a financial perspective. We will be better positioned to plan financially. In a sense, maintenance prediction helps manage both technical and operational efficiencies of software systems. Moving to the next slide about change prediction. Predicting changes in software systems is intricate. It requires a deep understanding of the system's interactions with its environment, of course. Systems tightly coupled with their environment tend to change frequently as the environment evolves. The factors influencing this dynamic include the number and complexities of the system's interfaces, the volatility of the system's requirement, and the business processes in which the system is utilized. So, these elements collectively determine the stability and adaptability of the system in the face of change. Predicting maintainability hinges on evaluating component complexity. Studies indicate most maintenance is concentrated on a small fraction of components. Complexity metrics can include the intricacy of control and data structures, along with the size of objects, methods, or modules. So moving on to the next slide, which is about software re-engineering. Software re-engineering is about modernizing a legacy system by reconstructing or rewriting it to improve the maintainability without changing how it functions. This is important. This approach is ideal for systems where only certain subsystems need regular updates. It's a strategic effort to simplify future maintenance and often includes updating documentation to reflect the restructured system. Moving to the next slide, which is about advantages of re-engineering. Re-engineering offers a significant advantage of reduced risk compared to new software development, which can face issues like development delays, for example, and staffing problems, of course. Moreover, it's usually more cost-effective, with expenses of re-engineering a system often being much less than those associated with building the new software from scratch. Moving to the re-engineering process. The re-engineering process for software starts with the original program. Through reverse engineering, we understand its workings and, of course, document the findings. Source code may be also translated to a more modern languages or platforms. The next step is called modularization, which involves breaking down the program into separate, more manageable modules. Simultaneously, we may improve the program structures, making it clear and more efficient. In parallel, data re-engineering is undertaken to update the associated data structures. The end result is a restructured program with a re-engineered data optimized for current technologies and maintainability. The re-engineering process includes a series of activities aimed at revitalizing legacy software. The first one is source code translation. This involves converting the old code into a new programming language that is better suited for the current technologies. The second step, or the second activity, is reverse engineering. Here, the goal is to analyze and understand the existing program to uncover its structure and functionality. Mostly, all the hackers stay in this realm most of the time. The third one is program structure improvement. This step focuses on reconstructing the program to enhance its clarity and understandability. Fourth point is about program modularization. In this activity, the program is reorganized into distinct modules, each handling a specific set of program's functionality. Number 5, which is the last point here, which is about data re-engineering. The final activity, which involves cleaning up and restructuring the system's data to align with the updated software structure. Moving to refactoring slide. Refactoring is akin to preventive maintenance for software. It's a process aimed at improving the program's structures and readability and reducing complexity, making it more maintainable. The key is to enhance the code without adding new functionality, focusing solely on making the existing code clear and more efficient. This proactive, approach helps mitigate the gradual degradation that software often experiences with ongoing changes. Moving to the next slide, which is about key points. As we have seen, software development and evolutions are iterative processes, often visualized as a spiral model. Maintenance often costs more than the initial development for custom systems. Evolution is change-driven, involving impact analysis, planning, and implementation, of course. Legacy systems, while it's outdated, still holds some business value. In this slide, it's obvious that maintaining a legacy system is usually more cost-effective and lower risk than building a new system. The business value and application quality should guide decisions on replacement, transformation, or maintenance. Software maintenance involves bug fixing and adapting software to a new environment and updating features. Moving to the next slide, which is about software re-engineering. Here, we see that software re-engineering aims to restructure and redocument existing software to facilitate easier understanding and modification. Refactoring is a maintenance strategy that involves altering a program to improve its internal structure while preserving, of course, its external behavior. Thank you for joining us on this journey through software maintenance and re-engineering. If you have enjoyed and learned from these videos, please show your support by liking and subscribing. Your engagement helps us create content that resonates with you. Feel free to share your thoughts and questions in the comments, and do not miss out the future content by hitting the subscribe button. Until next time, keep exploring the vast world of software engineering.